Hi, welcome back to this video series on Diffie-Hellman key exchange and in particular parameter selection that we have been talking about. In the previous session, I talked about this theorem that helps us to detect or test whether a given generator is indeed a generator. Given element G is a generator of a group. Okay. One precondition though is that we need to have the prime factors of the order of the group. Okay, then we can test it. So I wanted to quickly show you a demo of applying this theorem on a real published data, meaning the data from the RFC. This is RFC 7919. They have published PGQ. In this case, we have seen this several times. Q is actually a subgroup, and that subgroup is generated by the element G equal to 2. Okay, G equal to 2 is not a generator of this group ZP star. It is rather a generator for this subgroup of order Q. Okay, this is order Q. So we're talking about safe prime. You have given P, Q, and Z equal to 2. Can we apply this theorem and test it? In one moment, I will show you the demo. So I have copied and pasted those P, Qs, and Gs, and I'm just going to run it directly and then show you the outcome now. Okay. So I'll show you what I have in my Gs. Oh, let me set my G to be 2, right? And I set my P. What is my P? P is nothing but I have my P's and Q's, so I will just copy this, right? P's and Q's. It's exactly the same P's and Q's that you have seen in my demo earlier. So I'm just going to take the P's and Q's. Okay, so what I'm going to do is to show you that G equal to 2 is not a generator of this cyclic group. Okay, that's the first thing I wanted to do. So for that, I need to define something called order, right? Okay, so what is the order? Order is nothing but modulus minus 1 if our P is indeed a P prime, right? P is indeed a prime. We know that we tested it earlier. So order is nothing but P minus 1 that we know from the properties of the cyclic group ZP star. Okay. So what about the factors? Now we need to find the factors of the order. However, we are working with safe primes, right? In a safe prime, let me explain what are the properties of a safe prime. We have a structure like this, right? P and Q are primes, P equal to 2Q plus 1. So what is the order of the group? Order is nothing but P minus 1. So which is nothing but just 2Q, right? So what are the prime factors of order? Prime factors. It must be numbers 2 and Q, right? Because 2 is a prime number, so it's an even prime number, only even prime number, and Q is again a prime number. Therefore, you cannot split Q further. So the prime orders are just 2 and Q. Okay. All right. So I'm going to just plug in my factors. What are my factors now? My factors are basically 2 and P minus 1, right? Which is basically 2 and Q. So that should be good enough. Not P minus 1. 2 and Q are the factors of P minus 1. Okay. All right. So I have my factors ready. Now I should be able to run this. What about my modulus? Modulus is nothing but the prime P, right? Now we can call is generator function, right? It's going to test whether G is equal to 2 is generating a group of order of the given modulus and the given factors. Hopefully the answer is false, because we do know 2 is not a generator of the group ZP star. Okay, yes, it's false. Very good. Let's now reason about the case that we do know that Q equal to 2 is a generator for the subgroup of order Q. So how do we test that? So in that case, it's simple. Order is Q. Okay. What are the factors of order now? Well, Q is a prime, so there is no other factors other than Q itself, right? So there's only one factor. Okay. And what else we need? We need everything we have. So we can just call the print is order function, right? Order is Q, modulus is still P, so we don't have to change the modulus. The factors are basically, in this case, only one factor, Q. So let's try this. Yeah, it's true. All right, so we have confirmed that this data that they have given in the RFC satisfies the theorem, which is important. Otherwise, we have a problem. Okay, so the theorem says that if you know the prime factorization, you can just quickly test whether an element G is a generator or not. Okay, I use the word quickly. Why do I say that? Because all we are doing essentially is basically going through all the prime factors of the order, right? So how many prime factors are there for a given number? I'm not going to talk about a whole lot of details, but the number of prime factors is actually is nothing but the size of the number in binary. Okay, or in other words, if you know the a number, you just take log of that number, right? Log of order to the base 2. That will tell you the number of factors. Okay, that's as simple as that. Okay, so order finding the number of factors is not a problem. Meaning, what I mean by that is that if you know the number of factors, all you're doing is just having this little for loop, going through each factor and then checking whether this property is true, right? Okay, so we have to recall that computing power in a modular arithmetic is also rather quick. In polynomial time, we can do that. So I will talk about algorithms for computing power later, but at this point, all I wanted to show you is that this algorithm is extremely fast once you know the prime factors of the order of the group. Okay, so that's basically it. That's the end of this segment.